So once again, even though we are doing climate science, we are going to wander into climate change. So let's start with this one, which is showing the seasonal cycle of temperature over Earth. As you know, the heat capacity of land is very low, and albedo is very different based on whether it's a desert, it's a forest, it's a city, or it's a glacier, and so on. So you expect that land, especially at high latitudes, will have a large seasonal cycle. You can just average the difference, the average July temperature from the average December temperature to call it the annual cycle, the range of maximum versus minimum depending on which hemisphere you are in. So it's done that way here. So the summer minus winter for each hemisphere is shown. So as you can expect, middle of the land with cold temperatures show massive range of seasonal temperatures, 110 degree Fahrenheit over here, 90 degree Fahrenheit over here. And the main difference is that the ocean tends to be very moderated in its variability over the season because it has high heat capacity and it's deep and it warms very slowly and cools very slowly, and you can see the massive difference in the seasonal cycles going all the way here compared to, let's say, over here. The seasonal cycle here is at the same latitude is order 20 to 30 degree Fahrenheit here, and sorry, they are showing both degree centigrade and degree Fahrenheit for whatever reason. So land is shown in degree Fahrenheit and ocean is shown in degree centigrade, but each one has also, so 20 degree Fahrenheit, 7 degree centigrade, minus 7 degrees centigrade, and so on. So you can see that it's much warmer over here. This becomes very critical when we try to understand ocean circulation. So here it's 15 degrees centigrade seasonal cycle, and here shouldn't be minus, so it's 5 degree Fahrenheit here, so on and so forth. Okay, so Indian Ocean shows in degree Fahrenheit and Atlantic shows up in degree centigrade. I don't know why it's done this way, but nonetheless, just remember that land tends to have much larger seasonal cycle than the ocean, and we already talked about this before about how land and ocean contrast. So if you look at maritime weather in Eureka, California, is almost constant throughout the year with a very small seasonal variability, whereas land influenced place like New York, which is under westerlies, has a massive seasonal cycle compared to Eureka, going from negative temperatures in the winter to very warm temperatures in the peak summer months. Okay, so now we are warming on top of this, so we can look at the changes in surface specific humidity estimated from satellites. Dark shadings here indicate significant changes. So when you look for changes as in trends or difference, so this is trend in grams per kilogram per decade, there is statistical tests one can do to show that there are statistically significant changes. So for example, there are many regions where there are statistically significant positive trends in humidity, surface specific humidity, and there are statistically significant negative trends in some places. There are places where the trend is computed, but statistically you cannot show that it is significant. It's a kind of detail that matters in terms of saying how much things are changing. And this is the change globally averaged water vapor content. As we said, temperatures are warming over this period, so you can see that relative to a baseline, the temperatures, water vapor in kilogram per meter square per decade, are increasing over this period that we are looking at. Maybe you can say it's pretty flat here and it's increased over here, and there are year-to-year variabilities which are related again to things like El Nino and La Nina, which we haven't exactly studied, but I will briefly mention it at the end of this chapter. But this is just consistent with the idea that warming atmosphere holds more moisture. But the key question we asked before was where is it going to evaporate and where is it going to rain? So this is the surface humidity. So there are regions where the trend is negative, which means the lower atmosphere is drying, and there are places where it's getting wetter. So that again depends on the dynamics of how things work. Okay, so I will leave it at that, but it's more easier to look at ocean and other reservoirs in terms of their heat content increase from 1960 onwards to 2017 or so here. So you are looking at ocean heat content in the upper 300 meters in this line here. You are looking at 0 to 700 meters in this blue line, and ocean heat content down to 2000 meters is shown here. So the idea is that even if you look at the deeper ocean from 700 to 2000 meters, which is in this line, green line here, they are all warming here. So the deeper ocean, which had it takes time to heat for the heat to penetrate that far down, so it's warmed more slowly, but more recently they're all going together here in terms of the heat content change in let's say joules per meter squared per year. So this is something important to remember. Ocean obviously gets warmed from the surface, but we will see that there are also places where water sees the surface and then sinks or subducts under and gets away from the surface. That heat can remain there for a long time, as we saw from the age of water using C14, for example. We said the oldest waters are in the North Pacific, some youngest waters are in the North Atlantic, and so on, because of this circulation, which we will see again. So heat is penetrating the ocean, and ocean heat content is increasing at all depths. So this is something we must remember. So the increase is also accelerating. So if you look at different periods, 1960 to 2018, 93 to 2018, 2005 to 2018, and 2010 to 2018, you can see that the upper 300 meters has increased down to 700 meters. Each period is larger. 0 to 2000 meters, again larger over time. So the increase is accelerating. Just like the atmosphere is now warming faster and faster, the heat content in the ocean is also increasing faster and faster, which is not surprising because, as we already said, ocean takes up about 93% of the additional heat generated by the anthropogenic increase in greenhouse gases. This is in energy zettajoules. Ocean, this is allowing us to compare nicely. Ocean down to 300, 700, 700 to 2000, and below 2000, deeper than 2000. Land, ice, atmosphere, the residual that we cannot completely assign, and top of the atmosphere radiation changes from Ceres, which is energy budget satellite data, which is only available for the last a few number of years. So you can see again the ocean is taking up more and more heat down to even below 2000 meters, but in the top 300 meters and 700 meters and 700 to 2000 meters. Land is also storing more and more energy, even though land cannot store much energy because its heat capacity is low. It can cool and fast rapidly with seasons, yet over time land ground temperatures are increasing, and of course atmosphere accumulates some of that energy, but atmospheric heat capacity is very low. It's a very light fluid with very low density, so it cannot really have long memory. So almost all the memory is in the ocean, of course. Okay, this means the energy is getting stored in the system. It's in the ocean. Eventually it's going to equilibrate, so we have a long way to go in terms of getting rid of this additional energy we have trapped by increasing greenhouse gases in the atmosphere since industrial revolution. So this is the energy imbalance we saw before, incoming solar radiation. This is looking at 1971 to 2018, and the numbers in parentheses are 2010 to 2018. So this is 0.47 plus minus 0.1 watts per meter squared for 1971 to 2018. And the smaller number, the acceleration is shown by looking at the shorter period 2010 to 2018. So imbalance has accelerated as well, and the required CO2 reduction to get rid of this energy is minus 57 plus minus 8 ppm. That's the amount of atmospheric CO2 that has to be removed to allow the outgoing long wave to increase by that much. Okay, so here is outgoing long wave. Total heat gain is 358 plus minus 37 zetajoules. I think zeta is 10 to the 22. Please check. Atmosphere has stored 1% since 1971 and 2% since 2010. Land has stored 6% of the heat since 1971, and actually has cooled because land use change, urbanization, deforestation actually increase the albedo, and more energy can be lost. And the ocean has gained 89% of this additional heat from 1971 to 2018, and 90% since 2010. And 0 to 700% is 52%, 700 to 2000 meters is 28%, and greater than 2000 meters is 9%. So this is how the system is trapping energy. This is what is causing global warming. This is what is causing all the impacts that we will look at, including extreme events and so on. So everything is driven by the solar energy, and the balance happens in a natural system where there is a certain amount of carbon cycling through the system, other greenhouse gases like methane and N2O. As our industrial activities, we have used a lot of energy, and all those energy sources are emitting greenhouse gases, and of course also land use change, agriculture, and so on. So that additional energy is estimated with these kinds of sources of information with some uncertainty, but there is no question at all that we have trapped significant amount of energy, and we have now a good idea of how much CO2 has to be reduced to bring back energy balance. And then we will see that there is also a calculation on how much CO2 has to be taken out to hit some of the global warming targets that we talked about before, like 2 degrees C by 2100 with some 67% probability, or 1.5 degrees centigrade with 67% probability, and so on and so forth.